The conference is now in presentation mode. Your line is muted.
And I'd like to thank everyone for taking the time to be with me today. My name is Lance Zurich, and I am the product manager for the Fischertechnik division over here at Studica. And today, of course, I'd like to share some information with you on the importance of project-based learning for an effective STEM education program, and of course, in particular, to tell you all about the special Fischertechnik STEM Lab program. Now, if you aren't familiar with this, this is a standards-based curriculum, and it involves inquiry, design, and problem solving that was especially created by noted educator and STEM expert Tom White. Now, the following presentation is based largely on a workshop which Tom conducted at the ACTE Career Tech Vision Conference in Atlanta, Georgia this past November. And we've added to it somewhat since then. But anyways, to begin with, if my screen will move. The question of the day is, what is STEM? Now, this, of course, may seem like a silly question, especially for everyone in attendance today, but in a way it's not. Now, of course, I assume that most of us know that the letters in STEM stand for science, technology, engineering, and mathematics. It seems like if you're like me today, you can't open an educational journal or even your email box without being confronted by almost countless mentions of STEM. STEM, STEM, STEM. It's almost to the point where you hear it and read it so much that it becomes kind of overwhelming. Everywhere we look, someone is saying we need to devote more time and resources to teaching our students STEM. And meanwhile, many educators may be thinking, but wait, haven't we been teaching STEM all along? I mean, we teach math, we teach science. What makes STEM different? And of course, it seems that almost anyone selling any kind of robotics set or any kind of technology-based product is telling you that their product is ideal for teaching STEM. But is it really? Now, the image I've borrowed here from the STEMexposition.com website provides what I think is a nice visual for how STEM education should be thought of. Now, that's because one of the things that many experts seem to agree on is that true STEM education is not about teaching subjects such as science and math in a vacuum. It's about teaching in a way where these subjects are integrated. It's about teaching science in a way that plugs into math, which in turn plugs into reading, that ties into physics, and so on. Now, showing how these subjects support and blend into each other. And it's also about teaching in a way that properly prepares our students with the essential skills and the background they need for the technology-based world we live in now, and of course to be able to take their place in the workforce of tomorrow. Now, that all being said, let's provide a little background on the subject. Now, the picture here is from a project that Tom White was asked to help out on last year, and it was called The Science of Golf, and it was used at an exposition sponsored by Chevron. Now, the purpose of this exposition was to find ways to get students involved with STEM. Now, as Tom pointed out in his original presentation in Atlanta, the problem too often with STEM education is that even when there is funding in place, teachers and administrators aren't always exactly sure on the best way to go about actually teaching STEM. Now, Tom feels that an ideal method to do so is by creating exercises like the one pictured here, and in this particular example, students are performing various tests on a golf ball in a wind tunnel. Anyway, it's to have them do exercises where certain results will occur. Students will have to discover why they occur. And the way they find the answers to these questions was through the use of hands-on, project-based learning. Now, according to an article in U.S. News and World Report from September 21st of last year discussing the state of STEM and jobs, a summary was provided of the results from 3 days of workshops and discussions at the first National STEM Education Conference in Dallas, Texas, which brought together some 1,600 people from hundreds of organizations. And one of the major conclusions agreed on was that hands-on learning that links math and science to the real world works best for all students. Now, Tom White was inspired in his creation of the curriculum for the Fischertechnik STEM Labs by two famous people, one of which you'll see here, which is, of course, Benjamin Franklin. And you'll also see Mr. Franklin's quote shown here from his 1749 volume regarding the education of youth in the state of Pennsylvania. And in here he indicates the need to prepare students properly so that they have the skills required to take their place in the workforce. Sounds very familiar, doesn't it? The other person that influenced Tom was Sir Philip Magnus. Now this slide shows a quote from Sir Philip where he notes way back in 1889 the significant difference in learning seen between students who are taught in the normal lecture-style classroom environment and those who get to experience hands-on learning via what was then referred to as manual training. Now what Tom took from these esteemed gentlemen was the need to tie science and mathematics together, as well as the need to provide an avenue for students to engage in the educational process, which results in real learning as opposed to just the way we've always done it, approach of lectures and standardized testing. Now the purpose of STEM education, well, to be successful, STEM education needs to provide three primary things. Capital, if you will, for our society, and it's not just according to us, but it's according to the bipartisan Congressional STEM Education Caucus, which is currently chaired by Dan Lipinski, a Democrat, and Roscoe Bartlett, a Republican. Now, those three things are, first off, scientists and engineers to perform the research and development to ensure we maintain our place as a country in the world order. Now, you've heard it before, and it isn't an exaggeration. This isn't just an educational concern, it's really a national security issue, because it comes right down to, do we want to be dependent on getting our technology from other countries, or will we create and control it ourselves? Simply put, will we lead, or will we follow? Now, we will also need technologically proficient workers who are comfortable with and versed in the skills required for the modern workforce. And this isn't just a concern for the employers who will need such workers. It's, of course, also a vital concern to those who would take their place in the workforce, because today's high-paying, high-wage jobs are all technology-based. And finally, it needs to provide for technically literate citizens who can approach the important decisions of today and tomorrow with an understanding of the world we live in. Now, once again referring to the article from U.S. News and World Report entitled The State of STEM and Jobs, the STEM problem in the United States is most clear when viewed against the gap we see between our high school students and those in China, South Korea, and much of Europe, or the huge volume of mid-level engineers being produced by a place like India. In short, as a nation, we're in danger of falling behind the pace of the rest of the world in this important area. And if you doubt that statement, consider the following changes we've seen in just the recent past. Now here you'll see China. Now China is expected to build the equivalent of the entire existing United States infrastructure over just the next 20 years. Now just think about what that means. We're talking about all the existing bridges, the dams, the airports, electrical systems, hospitals, mass transit systems, and so on. Now, not far behind, India will do pretty much the same thing over just the next 22 years. Or consider Dubai. In Dubai, it wasn't so long ago, 1970 in fact, when the tallest building was only 3 stories tall. Well, as you can see from these photos, that's no longer the case. Now, industry has changed dramatically over the last 100 years. We've gone from the assembly lines and repetitive behaviors of the past, where workers would toil in close quarters, each doing simple piecemeal tasks over and over and over again, to the present day where ever-changing technology demands that new and innovative solutions to problems must constantly be formulated. And, well, is being a hard worker enough? Well, another quote from the previously mentioned U.S. News and World Report article says, "The sweep of industries affected by the STEM skills shortage was revealing, from healthcare, energy production and distribution, and autos to the whole slowly renewing domestic manufacturing area, transportation, and agriculture. There are no more jobs that require a strong back," said Tom Luce, the force behind the successful National Math and Science Initiative. "We have to explain to parents and kids that 30 years ago, you could have a living wage job and not be STEM capable, but today, that is impossible." And STEM isn't just for rocket scientists either. Again, quoting the same U.S. News and World Report article, STEM isn't really about the rocket scientists, although a few more would never hurt. It's really about the middle class. It's less about the folks who would design the airplanes than the ones who would build them. The guys who used to pour the steel now have to know how to program and instruct a robot to do it. Of course, technology has changed dramatically. 50 years ago, computers filled a room or sometimes a whole wing of a building, but today it seems like almost everyone has a smartphone or another handheld device that exceeds the capabilities, the speed, the memory, and storage of anything we could have even previously imagined. There's also a big skills gap. Now, in order to keep pace with this constantly evolving technology, we will of course need a supply of workers who are up to the challenge. Now this slide shows some of the skills that our students and our future workforce will need, not only to compete on a personal level, but of course also for us as a country to compete on the world stage. For example, you'll need workers that are skilled in sustainable designs, that are familiar with cost-effective use of materials and infrastructure, that have a familiarity with process control, measurement, analysis and signal processing, presentation, decision-making, data logging, control systems, and so on. The next generation. So of course the question is, how are we doing as a country to prepare for all of this? Well, this is a map showing the potential graduation rates for all 50 states. The dark purple, dark blue area indicates expected graduation rates of 80% or above. The lighter blue purple area indicates graduation rates of 70 to 79% expected. And the tan areas indicate expected graduation rates of less than 70%. But, as Tom White pointed out in his original presentation, due to the way in which this map was devised, for example, they included students who were choosing to drop out of school now, but who claimed they would later pursue a GED as being potential graduates. The rates shown here are actually quite generous. In truth, it's probably fair to say that a good 30% of the student population is underperforming. Now, meanwhile, of course, right at the moment, 3 million job openings in the United States remain unfilled, and at the same time, our unemployment rate is hovering near probably about 8%. And this is primarily because the workers who are available to try to fill those positions just don't have the background, they don't have the knowledge, and they don't have the qualifications to do so. So while all this is going on, how has education changed? Of course, perhaps a better question would be, has education changed? 100 years ago, students were arranged in nice orderly rows. They listened to lectures given by a teacher who might share examples on a blackboard, and then they took tests to see how much they had retained. And today in many modern public schools, students still follow the passive model of sitting in rows, listening to lectures, and taking standardized tests. Yeah, you might have a few computers around, but in truth, not really much has changed. Now, here's something you've probably seen on the internet before. It's an example of how one clever student answered a common geometry question. Find x, circled it, well, there it is. Now, this, of course, seems funny and cute at the moment, but it won't be so funny when this student can't get a job that requires math skills, as more and more tech-based jobs will. The problem comes down to this. Too often, students encounter things in schools that just seem too abstract to ever be useful in their lives. No one's helped them to make the connections, and so what happens? They ask the same three questions, which come down to, why do I need to know this? Where am I ever going to use this? And, okay, what do I need to do to get an A? And the problem is here, by failing to help the students make these connections, we end up simply failing the students. Essentially, the current educational system is based upon the model created way back in 1907 with the help of the Carnegie Foundation. Now, back then, students were deemed as fit for college based on certain requirements that they had met. For example, how many years of math, or reading, etc., but all based on the needs of that society in that time. Now, back then, students would go to work in factories where they needed not to ask questions or solve problems, they just needed to know how to follow directions. Now here it is over 100 years later, and our needs are pretty much the opposite. Now we need students who can ask questions, and we need students who can solve problems. Now, of course, this all begs the question, is there a better way to do things? And we think there is. Which brings us to the Fischertechnik STEM Lab program. Now this program was created by Tom White, as I mentioned, and it was designed to incorporate the state-of-the-art Fischertechnik construction system with specially created curriculum to provide a comprehensive, project-based learning experience with the focus on addressing current educational standards. So what is Fischertechnik? Well, as you will see here, Fischertechnik is a flexible and innovative construction system. It was created back in the mid-1960s by noted German inventor Arthur Fischer, who's pretty much the Thomas Edison of Germany. And unlike other popular construction sets designed to simply stack, Fischertechnik was created with more of an engineering mindset. Now, the core building block is unique in that it allows attachment from all 6 sides. Thus, it allows for limitless design possibilities. Many of the parts slide together to lock in place, and the hundreds of different parts that are available help to address very specific design needs. Now, as you'll also see, Fischertechnik is used by middle schools, high schools, colleges, and universities all over the globe to explore STEM-related concepts, things like, of course, robotics, renewable energies, mechanics, pneumatics, and so on. And it's also been used by numerous companies, including Porsche, Daimler Chrysler, and BMW for doing industrial simulations and also for training purposes. Now, Tom White built his curriculum around Fischertechnik because he truly believes that Fischertechnik is the ideal construction set for an engineering-based curriculum program like this. Now, the materials can be used and reused. Things that are built can be taken apart and reassembled into something completely different. So really what this comes down to is it's much more economical than purchasing an expensive piece of equipment that might be used for 1 or 2 experiments or projects, but then you put it on shelf and until next semester's class. And it should also go without saying it offers limitless creative opportunities. Let me just get a drink here. Anyway, when Tom White put together the Fischertechnik STEM Lab program, he had several goals in mind. First, based upon his observation that various types of teachers all have different strong points. For example, when he looks at himself, he sees his own strong point as being the creation of curriculum like this, more so than conducting an actual lecture. So he focused on creating curriculum that would provide a broad foundation of tools for all types of teachers to be successful in providing this class, so that essentially they could really instead focus on the needs of the students. What it is a turnkey solution that would provide everything they would need in one place. Now, the curriculum was designed to provide a clear roadmap for both teachers and students, with the learning facilitated through the extensive use of projects and problems for the students to address. The goal was also to enable teachers to provide students with engaging curriculum-based projects that had an authentic objective in solving real-world problems and which contained embedded academics. Now, I'd also like to point out that the Common Core standards addressed in this curriculum are the current standards that are in place. Keep in mind that reading no longer just means reading and understanding literature. It also refers to being able to read technical documents. Likewise, meeting the current writing standards now also means a student should be able to write technical documents, and so on. Now, continuing, under this project-focused model, students are told upfront what they need to learn and understand, and they are provided with different tools and pathways to achieve this goal. Now, among other things, students must perform research, both in and outside of class, and they learn the documentation process. For example, they'll create a design brief, they'll maintain a digital engineering journal, things of this nature. And they're also going to collect data. They're going to learn firsthand how data acquisition works. They're going to learn how to process data, how to put the data into graphs and other formats, and so on. Now, students are given a technical literacy task driven by the project. Fulfilling this task will require them to gain the knowledge and tools needed to address it through research and exploration. Students will perform a series of specially designed enabling activities through which they will acquire the necessary science, math, and tech-based skills. They'll devise solutions to their tasks and create prototypes using the advanced Fischertechnik modeling system. Students will then create and install the programs needed to control their prototypes. They're then going to document every step of the entire project and formally present their findings, including a demonstration of the prototype. Now, currently, the Fischertechnik STEM Lab program is available in 2 different versions, one for middle school and one for high school. Now, first off, we're going to take a look at an overview of what's covered in the high school lab. Starting right at the top here, we have sketching and documentation, which of course means documenting the whole process as we just talked about, the trial, the error, all of that. Structures, learning about the basics of different types of structures and testing various designs. For example, learning about the structures of different roller coasters and what kind of physics are involved, things of that nature. Mechanical systems, for example, how do gears work? Electronic systems, learning how circuits work, how things are wired, and so on. Control systems, how they're used. Sensors, what do they do? How are they used? Etc. And it gets into the fundamentals of robotics and automation. If we look at the middle school project themes, now the middle school curriculum touches on many aspects which are covered in more depth in the high school version, as well as including some unique areas such as those regarding the conversion and storage of energy from various forms. Now, the emphasis in the middle school module is on providing the basic groundwork needed to be an informed and literate citizen in our modern technology-based society, and again, to introduce the themes that will be explored in more depth in the high school segment. Now we're going to look at the curriculum structure. The way it's set up is the curriculum structure for each of the programs, and this goes for each unit of the program that we're going to be looking at, the middle school or the high school. It's set up to first off give you the purpose. It will go over the concepts, address the student deliverables, provide assessment and evaluation tools, provide an outline, give you all the standards that are being met, provide an authentic project scenario, a daily teaching plan, supporting activities, and also resources. Now at this point, I think it would be more helpful to show you what the actual curriculum for the Fischertechnik STEM Lab program looks like. Now keep in mind again that each set, either the middle school or the high school version, contains a disk with the complete curriculum. Now right now, we're going to insert the disk for the high school STEM Lab into our computer. And just bear with me a second while I do the little screen switch. So hang on a second here. Okay, and Mark, if you could just type in the chat room box, let me know that you're seeing the high school STEM program, or Christy. Okay, perfect. All right. Anyway, when you first put the Fischertechnik STEM Lab disk in, what will initially come up is there's going to be a screen right before this, and what you'll see is on that screen, it's going to show you that there is both a teacher version and a student version, and also a place where you can access the ROBO Pro software, which is actually the software used to program the various Fischertechnik robotic models that you're going to build during the course of this work. Now, the student version of the program, the curriculum materials, is essentially the same as the teacher version. What it does is, of course, it subtracts the standards-related material and the rubrics and the other instructor-only material that you'll see here. So anyways, this is the main screen that we would see in the teacher's version of the program. And as you'll see here, everything is lined up just the way I mentioned before. You've got the sketching and documentation, the mechanical systems, the structures, introduction to electricity, and so on. So you've got these various areas that are here. Now, just to give you again an idea of how that, like I said, how that layout follows for everything, let's take a sample section. We're going to look at the introduction to programming here. So we'll start that off. And once it moves for me, okay, here we are. Now the picture here that you'll see at the top here, this is a graphic representation of the ROBO Pro software. Now as you'll see, it's designed to use icons that represent the different actions, which you of course can just arrange in a flowchart manner to create the program for your robot. And the nice thing about ROBO Pro is it's great because it allows students who may not have any prior experience with the programming of any sort to quickly become comfortable with doing so. Anyway, that's just to mention what you're seeing up there. But getting back into the structure of the units, and once again, this would apply to any of the units. The first thing that you're going to start off with is a section where there is the purpose of the project that we're going to be doing in that unit. And this is, of course, the section that spells out exactly why are we doing this, as well as, of course, what we hope to accomplish. So it's all outlined right there. Next, I'm jumping ahead a little bit, are the concepts. And this is where we outline all the concepts that are to be addressed, the big things that you're going to need to learn from this project, the things that are going to be useful and vital to understand and know, not just now, but 10 years from now. These are the big things, the big concepts that you really want to take with you. It's one thing to get through the unit, but these are the things that you're going to need to retain and that are going to be useful in the future. We then get into an outline. And this is where we spell out exactly what's going to be covered in this project. For example, being on programming, we're going to deal with different methods of writing programs. For example, flowcharts, word problems, state machines, program characteristics, open loop, closed loop, flowchart, etc. So it's all going to be spelled out there. Then, of course, you get into the standards. And this is where, of course, the specific standards to be met by this particular project section, this particular unit, are spelled out. And this is, of course, the educational justification for the whole project here. So as you see, we start off with the Common Core math standards that everyone's having to deal with right now. So all of the math standards that are being met are all outlined right there. Linear, quadratic, and exponential models, modeling with geometry, interpreting linear models, etc. You have the reading standards for literacy and history and social studies for 9th to 10th. You have writing standards for literacy and history, social studies, science, and technical subjects. You then get into the science standards. For example, here you have the NSES content standards for K to 12. And below that, you get into the standards for technological literacy. And then you get into the ISTE standards, the Technology Foundation Standards for students. And I will add that in some of the newer releases that are going to be coming out for the middle school section, we are going to be addressing the next generation science standards as well. So probably in the coming year with the new release of the product, you will see that showing up as well. Anyway, then we get to the assessment. And then here is, of course, spelled out how the student performance is going to be assessed. For example, looking at the general rubrics for literacy here, we'll take the argumentative persuasive rubric here. So basically you'll see here's an example where let's say we're looking at the student's performance and let's look at the focus of the argument and attempt to answer the problem, but the response lacks focus. That's not yet. If we're looking at answering the problem and stating a position but still weak, it's only getting there. Answering the problem with a clear and generally convincing and focused argument would be meeting expectations. Or fully answering the problem with a very clear focus and a strong and convincing argument is, of course, exceeding expectations. And these rubrics are, of course, included in each of the units to provide the parameters for assessing the student's performance. Anyways, working our way down. The next thing is we have the essential question. And this is the big idea of the unit. Why is this important? Now, how well students answer this question is how we see if they understand all the pieces. And underneath that is the student scenario. And this is the real-world scenario the student is given. And this is essentially an answer to where will I ever use this? For example, in this case, they were given the scenario of being a controller programmer at a programming company that specializes in designing elevators and writing the control packages for their clients. Now, in this scenario, they will be required to program the elevator to perform certain functions. For example, how will it respond to a call button being pushed on different floors at the same time? Which floor is it going to go to first? Well, the client requirements are all going to be spelled out in this section, and the students will be required to create a program to address these specific needs, but they're also going to have to create a prototype. And on top of that, they have to prepare a presentation for their fictional clients that's going to include a demonstration of the prototype and the program in action. And this is going to be for each of the units. So once again, they're always going to have a different student scenario and some sort of project they're going to have to address. Then you get into the daily plan. And this is where we spell out the expectations for the project. And you've got every day of activities is listed, and each day of the plan acts as a guideline. And it'll spell out specifically what we're looking at today and what we want to accomplish overall. And each day's activities, day 2 to day 3 to day 4, each day provides a building block towards the big project that students are going to be required to complete at the very end. You'll see there are different links in here. For example, when we mentioned some of the documentation they have to do, there's links to the engineering notebook. There are links to the design brief if you're not sure what that is, or an engineering report. You can go there and it'll tell you a little bit more about that. If for some reason you had issues with the software, and who hasn't had issues installing software at some point, you can go to a section about installing ROBO Pro, or if you're having issues with the drivers, you can access that. But anyway, each day as you go down, we'll have a different task that's basically addressed, or a different question to answer. For example, on day 7, the key question here is, how does my dishwasher know when the dishes are clean? Which, of course, your dishwasher doesn't know when they're clean, but it's programmed a certain way to go through a certain cycle for a specific period of time. And so students will learn, they'll learn that. You'll basically discuss that and what have you. And other things covered in this section, for example, will include how data is taken from a sensor and recorded, or taking program files from the ROBO Pro software we were talking about, putting them into Excel to be worked on, and then transporting them back, working on robotic positioning. And once again, each unit builds on the one before. So not only did each day's activities, day 12 obviously builds on day 11, and day 13 builds on day 12, but also each of these units, as we progress through either of the sets of curriculum, either the middle school or high school, each section builds on what's gone before, and each gets subsequently more complex. And at the very end, there's a big open-ended project where students must combine all the things they've learned and worked with in the units before. And what's nice about this is this really helps to reinforce for students what it's all about. So anyways, we go through all the days of activities here, and this is a slightly longer unit. This one goes for 35 days altogether. You get into then the vocabulary that's being addressed. So that's nice. You have vocabulary to deal with. You have resources. And there's a lot of resources that are included in each section, web-based resources that were very carefully selected. And one of the nice things is during the course of doing the lab, students will be required to do a lot of background research and reading as well. And as much of it's internet-based, one of the things they're going to be taught is how to find good information on the internet, as opposed to all of the very sketchy information you can find. They're going to be learn how to basically tell the difference between that. You have Word documents here that you can print out here. For example, if you needed the document on digital branching, you can access that from here. We won't go there right now, but basically you can download those. You also have PDFs that are accessible, and you have PowerPoints that are accessible. So that's all there. And just to mention over here too, as you saw, this section here comprises 35 days of activities. The way the programs are set up, because people often wonder about this, how much time do they cover? Are these just projects or what have you? The Fischertechnik STEM Lab program is designed essentially to offer you enough material so that you can offer an independent STEM education class. For all purposes, we think of it as being, if you had a period a day, which is essentially everybody does 50-minute periods, or most people do 50-minute classroom periods. This is so you can have a regular class 5 days a week, 50 minutes a day. At the middle school level, it's set up to essentially offer you a half a year of material, so essentially 75 academic hours. At the high school level, it's twice that. It's 150 academic hours. For all purposes, it is a full academic year of material. And that's just with the material, the basic material, the day-by-day plan that we're going through here, for example, in the programming section. There are different areas where you can add to that. There are little add-on things. There's a section on competitions we're going to get into in a minute that adds to that as well. So what we're talking about is at the base, you have, once again, 75 academic hours, essentially a half a year at the middle school level, and once again, a full year at the high school level. Anyway, let's go right back to the top here. Once again, this is the same for all of these sections. If you get into the sketching and documentation, you'll see that that's set up the same way. There's a lot of material here. You get into the purpose of the project, the concepts, the outline, the standards that are being addressed as far as math, the reading, the writing, the science, the standards for technological literacy, ISTE standards, the assessment, once again, the essential question, student scenario, the daily plan, all once again laid out, getting into the vocabulary and the other materials. Mechanical systems are covered here. structures, introduction to electricity, sensing systems, actuators, mobile robotics, automation and robotics. Other nice thing you've got here too, at the top here, we have some sample ROBO Pro programs. Basically, while the ROBO Pro programming software used with the Fischertechnik models is designed to be very intuitive, there's also included on each curriculum disk a zip file, which you can access by hitting right there, which contains sample programs for each of the Fischertechnik designed robotic models that students will be asked to build prior to work on their own robotic projects. For example, when we were just in the section where they're going to have to build an elevator, they're going to be given an example that they can pull with instructions, which I'm going to show you in a second, but they're going to be given a section where they can access instructions to build a very simple Fischertechnik elevator so that they can learn the process. They can learn how the subsystems are built and what have you. And then, of course, from that, they have to take the knowledge from that and the other things they learn in the course of doing that unit to build something that's much more elaborate, that they have to design themselves, that they're going to have to program themselves, but they're going to have at least a sample version to work with. So here's where you can access those sample programs. And it also, we of course, once again, have information on, for example, installing the controller, drivers, or configuring the controller, things of that nature. Also up here, Fischertechnik manuals. As I mentioned, there are going to be different sample exercises the students are going to be given throughout the course of the program, where let's say they might have to build some sort of a simple gear machine or something of this nature to learn about the way that the subsystems work. They can access, for example, the gears might come out of the mechanic and static section, or if they were working on some of those simple coaster models before they get into building something more elaborate, they would go to the dynamic section, what have you. So what these are links to the different complete Fischertechnik assembly manuals. These are the same ones that are found in the commercially available kits that we offer as well. But this way you have access to that, so you can once again familiarize yourself with the subsystems, familiarize yourself as a student with the way that the Fischertechnik system works, and then once again take that knowledge and build on it when you have to, of course, create your own designs and what have you. Now, the other nice thing that we have here, as I mentioned before, is competitions, because everybody loves robotic competitions. This is something we've added on by popular demand. It's a revision of the new version of the STEM Labs, and it now includes this robotics competition module. And the whole thing is that these are so popular and engaging with students that we thought that it's great to have a segment that tells you how you can use Fischertechnik to conduct your own competitions at school, as well as how to get involved with organizations like, for example, ROBO Cup Junior, which holds competitions at various locations across the U.S. and as well as across the globe. And the nice thing about this material is while you can use this material for, let's say, if you want to have an after-school robotics club or something of that nature, like every other part of the Fischertechnik STEM Lab program, this is designed to address all the same current academic standards that we discussed earlier. So it's more than just being another fun exercise. It's a great avenue for offering an engaging teaching experience that you can justify spending classroom time on, because once again, it's going to address different standards. As you'll see right there, the math standards and what have you. So it'll spell all that out, and you've got more material there on getting involved with different competitions and what have you. So on that note, just bear with me a second while we go back to our slideshow. Okay, and Mark or Christy, we see curriculum and structure on the screen there. Perfect. Thank you. Thank you very much. Okay. So jumping back ahead, we're at the Fischertechnik STEM Lab program. So once again, as we mentioned before, the curriculum disk included with each of these programs includes the sample ROBO Pro programs for reference models. It also includes PDF versions of selected Fischertechnik instruction manuals, as we just went over. Over here we have a list of which manuals are included with each. The high school and the middle school, of course, each addressing slightly different things, have different manuals that are included. And once again, the nice thing is that the students learn the Fischertechnik system by building sample models from these sets, but then, of course, they must design and build their own unique prototypes for each project. So if you're doing little groups of students, you should get a lot of different types of elevators that are being developed, for example, in that one section. Anyways, here are some examples of some of the simple Fischertechnik models. As I was mentioning the elevator, here's an example of the very simple basic one that they would be building just to learn how that works. There's an example where they can build a pinball machine. That's using the electro-pneumatic materials. There's also some versions of some stacking and sorting robots that they're going to deal with as well. And again, just to say it, this material is included here only to help the students address some of the more basic daily activities and to learn, again, how the subsystems work and how the Fischertechnik system works. They're going to, of course, use the knowledge to, basically where in the areas where everything isn't spelled out for them, as well as the larger cumulative project at the very end. And, of course, the robotic competition module that we just mentioned. So anyways, each STEM lab kit comes packed in its own plastic sorting box for organized storage, and it includes the complete curriculum disc that we just kind of took a preview look at. It's got the ROBO TX Controller, which is, of course, used for programming the robots that you're going to make. It includes the ROBO Pro software. It includes all of the required parts, so all of the various parts that you're going to need to have, the wires, the fasteners, the different sensors, the power supplies. For example, on some of the mobile robots, you need a battery pack. That's included. There's the charging unit. So everything you need is going to be all in there. And so the question comes up, how many kits would you need in the classroom? Well, per Tom White, he recommends ideally one kit per 2 students at the middle school STEM lab level. And what this is designed to do is basically to keep each student engaged and involved in the activity, as opposed to having, of course, a couple students just, actually working and the other ones just observing. So really what you want to do is you want to keep it at the 2 students per box level at the middle school level. When you get to the high school section, though, because of the more involved nature of the projects that they're going to be working on, you could actually get away with 3 or even 4 students per set, because there's going to be enough for them to do where they can kind of break up the activities and everybody can address different things. Ideally, though, of course, the smaller the group of students per set, the better. But anyway, with this in mind, the average classroom of, let's say, 20 students would use anywhere from 5 to 10 of the STEM lab sets, depending on the section, of course, middle school or high school, and the budget you're working with. And, of course, if you're going to have multiple classes using this, you would need to have that set for each class, basically because while there are certain projects that you're going to address in a single class period, a lot of what they're going to be doing is going to be building these larger projects that will take, could take a week, 2 weeks, 3 weeks, what have you, to build, where things are going to be obviously in transition, so you would need to have different sets for each of the groups of students who are using it. So in summary, each Fischertechnik STEM Lab program set contains everything you need. It's got all the parts, the software, and all the assembly instructions, and complete day-by-day curriculum. It doesn't involve any additional fees. Once you get the curriculum from us, we're not going to come charge you for it again next year. It is yours to continue using. It, of course, offers engaging, hands-on project-based learning, which is especially effective for teaching STEM-related activities. It contains curriculum designed to meet current academic standards, all the stuff that we're dealing with now, the standards including the Common Core standards for math, the new science reading and writing standards, the NSES content standards, standards for technological literacy, and of course the ISTE standards. And again, the program is designed to provide enough material for at least 75 academic hours at the middle school level and at least 150 academic hours at the high school level. Now at that point, I would have to say thank you for attending this presentation, and if you will bear with me a second, I will unmute you all.
The conference is now in conversation mode. All participants are now unmuted.
You can feel free to ask me. You have me here. Any thoughts on what you've seen of Okay, I'm assuming that everyone is interested in what you're seeing here. Well,
Lance,
if you do have any questions. Yes?
Lance, this is Andrew at TTA.
Yes, Andrew.
Instructor training, is there anything offered?
There is actually, we are working with Tom White at the moment to set up something. We're probably, at the moment, we don't have anything set up. A lot of this will be, once an instructor gets this, they should be able to look it over, and, a lot of this, they should be able to, it should be somewhat intuitive. But that being said, obviously, because people do like to work on this, we're probably going to try to set up something, whether it be internet-based or maybe in some areas we may be able to do something that's going to be more regional. I know, like with you guys, you've had some things where, like I know we've talked about teachers in Louisiana and what have you, where we're probably going to end up trying to work something on the regional level, whether it be something that Tom Wade is involved with teaching himself or one of his proteges. But we're probably going to probably announce something about that in the relatively near future. So that will be coming down the pike, and we know that for a lot of teachers, as much as, like I said, once again, a lot of it should be somewhat intuitive, but obviously people like to have that, that safety net, become familiar with it, get hands-on with it, work through it. So we're going to set up something like that. Yes.
Okay, thanks.
Okay. Anyway, once again, want to thank everyone. If you don't have any questions this time, thank you for attending the presentation. Of course, if you do have any questions after that you didn't want to address right now, you can either email me at the one email address you see down here, which is, of course, stemlab@studica.com. Easy enough, STEMLAB@studica.com. You could also email me directly. Actually, I'll get you the email, don't worry. But you can email me directly if you'd like, which is Lance Z, that's LANCEZ, @Studica, STUDICA.com. You can, of course, call us and speak to one of us personally. Our number in the U.S. is 888-561-7521. If you're calling from Canada, you can, of course, call 800-561-7520. And, of course, you'll see the URL if you'd like to read more about this. It's www.Fischertechnik-STEM-lab-program. So once again, on that note, I thank everyone for attending, taking the time. If you have any questions, like I said, if you would like more information, if you'd like us to send you some of the PDFs we have on this, just shoot me an email. Shoot us an email at the STEM Lab email address there. Also, we have been recording this presentation, and we hope to have a recording posted in the very near future. So everyone who's in attendance, we will send you a link for that. Once again, I thank you very much for coming along, and if you have any questions, please let us know. So on that note, have a great day, and we hope to talk to you soon. Take care.